Hello, welcome to another module. So in this module, let us start looking at M-ary, another digital modulation scheme, right, based on M levels, termed as M-ary pulse amplitude modulation. Okay, so we want to start looking at M-ary pulse amplitude M-ary pulse amplitude modulation, which is based on M levels. Until now we have seen binary modulation schemes. So this is based on M levels, which we are going to describe shortly. Okay, and this is abbreviated as M-ary pulse amplitude modulation is abbreviated as PAM. M-ary PAM, M-ary pulse amplitude modulation. So in this modulation scheme, if you can look at, if you look at the waveform xt, let us consider the waveform xt equals a naught times pt. This is our waveform, the digital communication waveform. Now this a naught can take one of m different levels. So far we have seen, correct. So one of m different levels. So far what we have seen is a naught can only take at most one or two levels, that is binary, plus a or minus a, or a or c, correct. Now we are going to see a general modulation scheme, a more general, right, in fact a more capable modulation scheme we can also say, as we are going to see shortly, which can take not one of two levels but one of m possible levels. So each symbol a naught, each digital symbol a naught can take one of m, capital M possible symbols. Okay. Now let us represent these m symbols. Now therefore since there are m symbols, the number of bits equals log m to the base 2. For instance, if we have 2 bits 0 0 0 1 1 0 1 1, these can be mapped to 4 different levels. So this can be your level 0, this can be your level 1, this can be your level 2 and level 3. So we have 4 levels, implies basically m equal to 4. Therefore number of bits, as we can see, is log 4 to the base 2 equals 2. So we have 2 bits or 2 bit words or 2 bit words. Okay. So in an M-ary constellation we can achieve log m to the base 2 bits per symbol, that is each bit, each symbol conveys log m to the base 2 bits, log m to the base 2 bits per symbol. For instance, example, let us take a simple scenario where m is equal to 8, implies number of bits naturally equals log 8 to the base 2, this is equal to 3. If you look at the m levels, you can either be a, these are equispaced, 3a, 5a. So we are generalizing this concept from a and minus a, we are allowing m possible levels minus 7m. So what we have is we have 8 possible levels, 8 possible levels. Okay. Now, A naught can belong to one of these 8 possible levels, that is plus or minus A, plus or minus 3A, plus or minus 5A, and plus or minus 7A. Okay. And the distance between these levels, if you can see the distance, we are keeping a constant distance between these levels. Distance between levels is equal to 2A. The distance between the levels is equal to twice A. So, we have 8 levels, we are considering an M equal to 8 constellation, which means there are log 8 to the base 2, 3 bits per symbol. The levels are plus or minus A, plus or minus 3A, plus or minus 5A, and plus or minus 7A. Okay. So, this is an M-ary, that is 8-ary PAM pulse amplitude modulated constellation. Okay. Now, in a general, for an M-ary constellation, in general, for general M-ary PAM, we have A naught equals either plus or minus 2I plus 1A, where I equals either 0, 1, 2 up to m by 2 minus 1. Naturally, this is defined only for m is even. Okay. So, m is even. Okay. And number of bits per symbol is log m to the base 2. Which we already said, log m to the base 2, that is the number of bits per symbol. Okay. Now, we have to compute, as we have seen several times before, we have to normalize things such that the average bit energy or average symbol energy is same. Now, since we have more than one bit per symbol, let us start with the average symbol energy. Alright. So, let the average symbol energy be denoted by ES. Okay. So, let average symbol energy be equal to ES. So, we have ES by symmetry, ES is equal to, if you look at energy of symbols on the right of 0 greater than 0 is equal to energy of the symbols on the rest of 0. So, I am only going to look at half of the axis, this is by symmetry, I am only going to look at m by 2 symbols, because energy of the symbols by symmetry, okay, this is by symmetry. Energy of the symbols greater than 0 is equal to energy of the symbols less than 0. Okay. So, this is equal to I equal to 0 to m by I equal to 0 to m by 2 minus 1. As we have seen, this is plus or minus 2I plus 2I plus 1 whole square times a square. Since we have well, A naught equals, that is considering symbols greater than 0, A naught equals 2I plus 1 A. Of course, for less than 0, that is when it is minus 2I plus 1 A, the energy is similar, the energy is identical. So, that is why we are only considering half of the symbols, that is symbols corresponding to plus 2I plus 1 into A. The rest of the symbols, that is for each symbol plus 2I plus 1 A, we have one symbol which is minus 2I plus 1 times A, which has an identical energy. Okay. Now, this is equal to, let us simplify this average energy, because this is the most important step. So, this is equal to, well, 2A square divided by m summation I equal to 0 to m by 2 minus 1 4I square plus 4I plus 1, this is 2A square divided by m. Now, here comes the important part, m by 2. Now, 4 summation I square. Now, we will remove the summation. So, 4 summation I square would be 4 times from 0 to of course m by 2 minus 1, that would be 4 times m by 2 minus 1. Summation of squares up to n is n into n plus 1 into 2n plus 1 divided by 6. Here we have summation from 0 up to n by 2 minus 1. So, that is m by 2 minus 1 into m by 2 minus 1 plus 1. So, that is m by 2 times 2m by 2 minus 1 plus 1. So, that is m minus 2 plus 1, that is m minus 1 divided by 6. Okay. So, these you should be able to get, these you should be able to evaluate from standard expressions. So, this I am not going to repeat this because you are expected to know this you evaluating from standard expressions for summation of I square, okay, I equal to 0 to m minus 1, these expressions are standard, okay, plus, well, 4 times summation I. So, summation I 0 to n is n into n plus 1 divided by 2. So, up from 0 to m by 2 minus 1 is m by 2 minus 1 into m by 2 minus 1 plus 1, that is m by 2 divided by 2, plus summation of I equal to z, summation of 1 I equal to 0 to m minus 1 is simply m by 2, that is 1 added m by 2 times. So, that component is simply n by 2. Now, we are going to simplify this expression to compute the average energy. Okay. So, this can be simplified as, well, 2a square divided by m, you can check this, this is 2 by 3 times m square by 4 minus m by 2 times m minus 1 plus m into m by 2 minus 1 plus m by 2, which is equal to 2a square divided by m into 2 by 3 m cube divided by 4 minus 3 m square divided by 4 plus m divided by 2 plus m square by 2 minus m plus m by 2, that is minus m by 2. And if you now simplify this further, what you will have is 2a square divided by m into m cube by 6 minus m by 6, which is equal to 2a square divided by m into m by 6 into m square minus 1, which is equal to, well, a square divided by 3, sorry, a square divided by 3, a square divided by 3 times m square minus 1. So, we have the final result that ES, average symbol energy, as a function of A and M is a square by 3 minus m minus. So, this is the average symbol energy, or you can also say average energy per symbol, okay, and this is equal to, this is a function of A and M. Naturally, it depends on A, where 2a is the spacing. Now, we cannot say A is the amplitude, because there are several amplitudes A, 3a, 5a, so on. So, we can say, we can only characterize it by the spacing between these successive levels, and the spacing is basically given by 2a. So, this is a function of A, which is the spacing, and also M, which is the number of levels, that is the point. So, function of A comma M, where spacing is equal, spacing between levels is equal to spacing between M-ary PAM levels is equal to 2a. Okay, spacing between M-ary PAM levels is equal to 2a, and therefore, now look at this, we have ES is equal to, well, a square by 3 into m square minus 1. If we are given ES, therefore, if we set A is equal to 3 ES, remember that is what you want to do. We want to choose an appropriate A where 2A is the spacing, 3 ES divided by m square minus 1 square root. So, setting A equals square root of 3 ES by m square minus 1, this ensures average symbol energy of ES. So, setting this value of A, this ensures average symbol energy of this ensures an average symbol energy of ES, that is the whole point. Okay. And therefore, now we have got what is the A, what is the parameter A, where 2A is the spacing between these two levels. Okay. We also know that our waveform xt equals A naught times Pt. Okay. A naught is plus or minus 2I plus 1 times A, 0 less than equal to, I can take the values 0 less than equal to I less than equal to m minus 1. Now, you can choose any pulse Pt. In particular, one can choose the pulse Pt, which is square root of 2 over t cosine 2 pi f c t. We have seen that this is basically seen several times before. In fact, this is basically where 0 less than equal to t less than equal to k over f c, that it contains an integer number of cycles, and we have seen that energy of this pulse, when you set the pulse like this, energy of the pulse equals E p equals 1. The energy of the pulse is unity. When you set it like this, the energy of the pulse is unity. And obviously, now we have a pulse Pt, therefore, I can use the matched filter receiver. Okay, that is also similar to what we have done before, which is the matched filter receiver. Add the receiver. So, receiver operation, receiver for M-ary PAM. So, obviously, we are again going to use the matched filter, H t matched to P t, which is equal to, that is again the same. Matched filter maximizes SNR, because for the, if you go back and look at the derivation of the matched filter, we did not assume any particular modulation, we have only assumed a pulse shape and a symbol A naught. A naught need not belong to any particular modulation, alright. So, for any given pulse shape Pt, irrespective of the modulation scheme A naught, the matched filter maximizes the SNR. Therefore, we are choosing the matched filter Ht, which is P capital T minus T, where capital T is the symbol duration. Okay. So, that remains unchanged. So, matched filter still maximizes the output SNR. Okay. And in fact, once you matched filter, so we have Ep equals 1. In fact, once you matched filter and sample, you have again Rt equals A naught plus n tilde, Ep equal to 1, which is equal to A naught plus n tilde, which is very similar to what you have obtained for binary phase shift keying. Only thing is A naught changes. The only thing is now A naught equals plus or minus 2I plus 1 A. So, that is the only difference. So, you still have A naught times Ep, Ep equals 1. This is Gaussian noise. Again, the noise part is exactly the same as what we have BPSK. Gaussian noise, mean equal to 0, variance equals A naught by 2 EP, where EP equals 1, this is A naught by 2. And of course, we are assuming Gaussian noise, assuming the input noise process, we are assuming, or let me assuming input noise process assuming that the input noise process is Gaussian, wide sense stationary, 0 mean. Of course, when the Gaussian noise process is wide sense stationary, it automatically means it is strict sense stationary also, we have seen that, or follows from the properties of random process with R n and tau, that is 0 R n and tau equals n naught by 2 delta tau. Basically, this is white noise, additive white Gaussian noise, the same thing. Okay. Additive white Gaussian noise. Okay, that is the same thing. Okay. So, this is basically, again let me clarify, this is after match filtering and sampling at t equal to tau, t equal to capital T. After match filtering and sampling at t equal to t. Okay. Now, let us come to the probability of error, the discussion about probability of. Now, this is going to be slightly interesting, it is going to be different from what we have seen, because the modulation scheme is complicated, it is going to be slightly different than what we have seen for BPSK and other modulation schemes. Okay. So, the probability of error discussion, as I was just saying, is going to be slightly more different and of course, more complex, because the modulation scheme is complex, naturally the analysis is also going to be complex. It is going to be different from what we have seen earlier for BPSK. BPSK, it was still fairly simple. So, this is going to be slightly more complicated, because the nature of different points in this constellation is different, because if you look at these points on the line, some of the points are in the middle, surrounded by, or basically flanked by a point on each side, some of the two of the points precisely are on the end. So, the probability of error for each of these things, or the average probability of error for each of these, considering the transmission of each of these symbols, is going to be different. That is the point I want to emphasize. Okay. So, what I am saying is basically, first of course, we have to come to the decision rule. Let us talk a little bit about the decision rule. Now, we have the levels A, for instance, let us again consider our m equal to A case, because that is simple to handle, or let me just be a minus A minus 5A and minus 7A. This is your m equal to 8 PAM. Now, again once again the detection is very simple. If you look at this point A, interior point A, by symmetry, you can look at the midpoint between A and 3A, and you can look at the midpoint between minus A and. So, this midpoint is 0, this midpoint is 2A. So, if RT lies in this region, that is, we are using something very similar to BPSK again, if you think about it, we are looking, because it has two constellation points. So, if RT lies in this region, decide A naught is equal to A. Now, the point is in BPSK you have only one point. So, you look at the midpoint between the 2 points. Now, here you have a point, there is a point on one side, there is another constellation point on the other side. So, we have to basically look at two midpoints, one on each side. So, the midpoint with respect to 3A is 2A, midpoint with respect to minus A is 0. So, if RT lies in this range 0 to 2A, correct, then one can decide A, and similarly for all the interior points. So, again it is fairly simple by symmetry, again one can again say by symmetry if 0 less than equal to RT less than or equal to 2A implies decision equals A. Okay. 0 less than or equal to, or not 0, but now if you look at the midpoint, this other set of midpoints 2A and midpoint between 3A and 5A, that is going to be, that midpoint is going to be 4A. So, in this region we obviously have to decide A naught equals 3A. So, if RT 0 less than equal to RT less than equal to I am sorry, again not 0, this is if 2A less than equal to RT less than equal to 4A implies decision equals 3A. Similarly, for the negative side, of course you have this positive side. Similarly, for the negative side, again it is symmetric on the negative side. So, minus 2A less than equal to RT less than equal to 0 implies decision equals minus A, and so on and so forth. So, one can proceed by symmetry. I think this is the complete. So, there are going to be M decision rules naturally for the M constellation points. It is going to be a combination of M cases, let us say, let us not say there is only one decision rule, it is going to be a combination of M cases. Combination of M cases, one for each point, similar to what you have in programming, any programming language where you have a case and depending on a case there is an outcome. So, you have different cases, that is depending on the boundaries or the box in which RT lies, one has to choose the appropriate value for A naught. Now, obviously another interesting aspect you can see here also here is that you can also call this as a nearest neighbor criterion, because if R lies in 0 to 2A, then the nearest neighbor is A, that is it is closer to A than it is closer to. So, this can also be called, so if R lies, so one thing you can observe here is that in this region closest neighbor is A. So, this decision rule is basically you are taking RT, looking at what is the closest neighbor and assigning it to the closest neighbor. So, this can also be called as the nearest neighbor decision rule. Okay. This is a very important criteria, nearest neighbor, that is we are assigning RT to the closest constellation point. You can check this. Okay, so we are assigning RT to the closest constellation point. Okay. So, that takes care of the interior points. Now, what happens to the other points, that is the end points, because they are special. You can see each interior point has 2 points, one on each side. The end points, that is if you can look at the corresponding to I equals m by 2 minus 1 and I equals minus m by 2 that is corresponding to I equal to m by 2 minus 1. These 2 points, that is 2I plus 1 minus of 2I plus 1. Now, these 2 points have only one neighbor. Of course, the point on the rightmost has one neighbor on the left, point on the leftmost has one neighbor on the right. So, the analysis, so the decision rule with respect to these 2 points is going to be slightly different, which we will look at in the next module, and also the corresponding analysis for the probability of error. Thank you.